visible.
So, hello everyone, this is Devabrata Boni. So, today I'll be taking a short session on some interview question. This will be a demo session. So, this session will be based on some of my interview experience from companies like Synopsys, NVIDIA, Qualcomm, and Analog Devices. So, I'd just like to thank Rajat for giving me this opportunity. And I'll also like to thank VLSI for all for conducting this session. In the middle, if any people have faced any problem or wanted to share something, please feel free to ping in between. You can also use the chat section. So let's get started. So like in most of the interviews, like this flops, and in digital interviews, this flops is one of the most important concepts. So most of you people might have heard about like the questions, for example, um, how to use a mux to construct a logic gate, how to use 2:1 mux to make an AND gate, XOR gate, and all those kind of things. So those all things are available in the internet, Google, and YouTube also. So I have tried to make a different question. So this is a bit tricky one. So let's discuss this question in details. So, so basically, I guess most of you know what a flip-flop is. Like, is there anyone who doesn't know what a flip-flop is? Please respond, someone.
Yes, sir.
Yes, sir, we know.
Okay, fine. Oh, so just I wanted to ensure you whether you all are there on the line or not. Okay, fine. So like a JK flip-flop, what happens in a JK flip-flop is, let's say, uh, the present state. Let's say there are two inputs basically, J and K. Can you please ensure that? Can you please confirm? Is my paint screen visible?
Yes, sir.
Is the paint screen visible?
No,
See
sir.
my
No,
page?
sir. No, sir.
Okay. I guess now it is visible.
Yes, sir.
Yes, sir.
Yes, sir.
So, and by the one more thing, you need not, you don't need to call me sir. You can call me by my name. Okay. So let's continue the question. So the JK flip-flop states that if the present states are 0, 0, then whatever is the value that is present in the flop, that will be remain same. That will remain same. So that Q plus means the next state and Q means the present state. So the next state will be equals to the present state if J and K both are 0. Okay. And this is also, and one thing to note, that we must pulse the clock for this event to happen. And the second thing is that if J is 0, K is 1, and if we pulse the clock, and whatever is the present state, the next state will always be J. If we pulse the clock again, but if the input is 1, 0, then the next state will be always 1. And in the last case, if both are 1, then we just call it as a toggle state. The next state will be inverted version of what is there in the present state. So this Q bar means the inverted version, and plus means the next state. So this is what a JK flip-flop means. Now I will just come back to the question. So we have to construct a JK flip-flop. We are given a D flip-flop, a 2:1 mux, and an inverter. So how to approach this problem? We all know a D flip-flop, right? The equation of D flip-flop is the next state is always equals to the present state. This is the equation of a D flip-flop. So let me erase my screen. new one. So it's a D flip flop. We have given D flip flop. So what we need to do is like we have to characterize the JK flip flop here using a D flip flop and then inverter and a 2:1 multiplexer. So I guess most of you are aware of what a multiplexer is, what an inverter is. So how to approach this problem? Any idea? Someone can say any idea or like how to make a JK flip flop using these three.
तो ये उससे बेसिक लेवल है ना इंटरनेट से बोल रहा
Recording in
Sorry, I cannot hear you. Can you please speak louder?
Sir, first we change D flip flop into SR, then using NOT gate, applying NOT gate in between input and clock, and after that SR we convert into JK by using 2x1 mux.
Start to JK using 2x1 mux. No, but the question is like you can only use one D flip flop, one inverter, and one multiplexer. You cannot use anything else. You can convert this flip flop to whatever you want, but the criteria is that you can use only one inverter and only one 2:1 multiplexer. Nothing else. Did you get my question?
Yes, sir.
Okay, so can you please think again? Like if you convert into SR flip flop, then we need some AND gates, right? Or NAND gates. So I will wait 2 minutes for some of you to think and respond if possible, or else I will proceed.
Can we do like this, like realizing the NOT gate using mux, and then providing a feedback to the mux which is in NOT gate, then it will act as a buffer. So buffer is basically a D flip flop. So we can realize D flip flop using mux and NOT gate, and then using that which we have got the circuit, we can make a JK flip flop. So here we'll be using NOT mux, using both we'll be making a D flip flop and then JK.
So basically, you mean to say that we already have one D flip flop here available. So you mean to say we want to make another D flip flop using these two, and
Yes,
then
sir.
make a JK flip flop? Can you tell me how to make a JK flip flop using these two elements?
So basically, we can make a NOT gate using mux. So in order to make a NOT gate using mux, what we do is we just
We know that we can use a mux to make a NOT gate. For example, if I take this mux,
1 and provide it as a select line as a select line is B.
so select line if you get A,
Yes,
if
sir.
A
Now
is
this
0,
will be,
then 1
now
or else 0.
this is acting as a NOT gate. So
This is active or not?
yes. Now if we make a feedback to this mux, then it will act as a buffer.
Use feedback. This is not good. Like this one. Why do you want to make a buffer? First, tell me.
In order to convert that circuit into a D flip flop, because basically D flip flop acts as a buffer. Whichever is the input, that will be getting in the output.
Correct. But our aim is to make a JK flip flop using these three elements. This is the question. We have to make a JK flip flop using a single D flip flop, a single inverter, and a single 2:1 multiplexer. So you have, so the question is, you have J and K as input.
Sir, can I tell?
Yes, you can tell. So you have to do something using these three elements, and so that
Yes,
you will
sir.
get the output as Q.
So take first 2 into 1 marks and connect the select line as Q. That is present the state output Q, and the I1 as K not get.
I1 as K not get. K not
K bar,
K,
basically
K bar, हाँ. K bar, हाँ.
and I not as J
I not as J.
and select line as Q.
I not as J.
And
Select
select line as
line.
Q.
Select line as
as
Q.
Q, and then connect the output to the D flip flop. D input. Then it will get a J flip.
Fine. So let's discuss the problem. I think the answer is correct.
Yes, sir.
So you have two inputs J and K. So first let's analyze this problem. Okay. Let me take a new screen. So you have J and K as input. So you have J. Here you have K. Okay. Now the situation is that if J is 1 and K is 1, both are 1, then you have to toggle the input Q bar. And from where I will get this Q bar, I'll get this Q bar from the D flip flop. So let's make use of the D flip flop that is present to us. And let's also take use of the multiplexer. Now, so the solution that one of the guy mentioned is like we have to do something with this multiplexer as well as this D flip flop, and we have a NOT gate here. So like for example, let me try connecting few things. Let's say if I connect the J and K to this input multiplexer, then based on the select line, can I do anything? Like for example, if I connect this select line, so like we have to make use of the table, right? So let me write the table. So if the input is 0 1, then the output should be 0. If the input is 1 0, then the output should be 1. Or if it is 0 0, the output should remain same. So let me try connecting it straightforward. Since we need to retain this state, so we need to use this Q. So for example, if this Q is 0, and if J and K is 0 0, then the output should also be 0. So if I connect it here, then this equation is satisfied, the last equation. If the input is 1 0 and if the Q is 1, then my output should be 1. So let's say my input is 1 and 0. My Q is 1. If my Q is 1, then I'm getting 0 as the output. That is not correct. So, but if my input is 0 1, let's say my input is 0 and my input is 1, and my present state is whatever be the present state, let's say 0 or 1. So if my present state is 0, then I'm getting 0. But if my present state is 1, then I'm getting 1. That is again a wrong thing. So I have to do something with this k. So let me add this inverter here. Now, if I add this inverter here, my these two equations are solved. Now let's come to the last equation and check whether this problem solves this equation also. So if my both the inputs are 1, 1, and let us consider key q is 1. So if my q is 1, then I will get a 0 here because there is an AND gate, and that is the toggle state which you want, q1. If my q is 0, then I will get 1, then I will get 1 here. This is the toggle state here.
Hello.
So
Yeah,
this
ठीक
is
है.
the basic construction which you have to play with. So the first thing that you can do is like you have to connect J and K to the multiplexer. Like if you connect JK to the D, then it doesn't make any sense because you already have a flop. So first what you need to think that can I connect this J and K to this multiplexer and choose the select line as some input or output of this flop. So because we have to control this flip-flop using this J and K inputs only. And we are given an additional NOT gate so that these three equations are satisfied using this NOT gate. So is the problem clear to everyone? Is the
Yes.
solution clear to everyone?
Yes, sir.
Okay, fine. So let's move on to the next question. Okay, so the next question is related to a state machine. So you might all be knowing what state machines are, or if you don't know state machine, then I will take another session having a detailed discussion. So the state machine is also. Hello.
Sir, please start.
I cannot hear you. Can you be a bit more louder?
We can start, sir.
Fine. So let's start another question. So this state machine is also a very important topic in many of the interviews. And this question is also a very specific question, interview question, not directly asked, but this can be asked some in a very indirect fashion. It depends on the interview. So the question is like we have to make a state diagram for a circuit that outputs 1 if the serial binary input is divisible by 5. So like the interview will tell you that draw a circuit in which you can detect a divisibility by 5. So let's say you are driving an input, let's say 101. So 101 in binary means 5. So if you drive this 3-bit input 101, then you should get an output as 1. If you drive any other input like 110, that is 6. So you will get the output as 0. So this is the circuit that you have to make, and you just have to make the state diagram. And if you can draw the state diagram, then making circuit is not a very big deal. So let's start the solution. If anyone wants to suggest any ideas or way to solve this problem, he can. I'll just wait 2-3 minutes. Is the question clear? You have to draw a circuit, or you have to draw a state diagram. You are giving input as 1 or serial bit input. Let's say 1 0 1 1 0 0, whatever. And this output will only be 1 if this number is divisible by 5. Is the question clear?
Yes, sir.
So does anyone wants to comment any solution on how to proceed this state diagram?
Sir, please again repeat this question.
Fine. So like what state machine is like the first of all, the interviewer will just ask you to draw a circuit diagram or draw a, logic diagram based on this. He will not tell you the term state diagram. So first of all, you have to understand that this is a question related to the state diagram. So like here we are driving many data, is serial data coming one by one, 0, 1, 0, 1, 0, 0, whatever the data is. Let's say you first drive 0. So when you will drive 0, you will get nothing. You will get the output as 0 because this 0 is not divisible by 5. Then let's say you drive 1. This 1, 0 by in decimal means 2. 2 is also not divisible by 5. So in the second clock cycle, you will also get the output as 0. Then let's say you drove 0. Then also you'll get the output is 0. Then let's say you drove 1. You drive 1 into the input. Now this 1010 value is 10. And 10 is divisible by 5. And then you will get the output as 1 because this 10 is divisible by 5 in the 4th clock cycle. Let's say you again drive a value 1. Now this is not divisible by 5. So you will again get 0. So you have to construct a machine such that the input number coming serially is divisible by 5. This number can be anything, like this 5 is a very easy one. So I have taken this number. 3 and other numbers are a bit trickier to solve. So is the problem clear now? And this input is coming one by one. You have to give the output one by one. So you have to use something which you can store the values. You can store these inputs. You can store the information of this one input coming one by one so that you can analyze those information and use the next input coming at the MSB side to produce the output. So you definitely need some sequential elements and storage elements. So it is basically so you have to understand that this is a question of the state machine. You also definitely need some way to store this information and process. And the most efficient way of solving this question is by first drawing a state diagram. So what a state diagram looks like is that what is a state diagram is basically there are two types of state machine. One is the Murray and one is the Mealy one. So in Murray machine, the output of a state diagram depends only on the input of the state input of the state. And in Mealy, the output depends on the input as well as the present state. So let's say you have a flop. You have a flip-flop. I hope you all know what a flip-flop is. So in this case, this Q output depends on the input D as well as on the clock also. So let's say this flop is storing a value 1. Now, if you give some input 0 and pulse the clock, this 1 will become 0. So this is storing an information, and if you change the input, then the output will also try to change based on the input. So this is a Murray machine. And similarly for Mealy machine, it will be a bit different because then let's say if you use an AND gate here and use this input as like this one and produce it in the. So now the output depends on the input as well as on the Q value. So now this is a Mealy machine because the output will also depend on this input of two AND gates, and this will depend on the Q as well as on the input. So this is basically a state machine. So let's now try to solve this problem. So we generally represent state machine by, let's say, circle. Let's consider states. Let's say we have considered. So like how to solve this problem? We have to figure out a way so that we can use that this number is divisible by 5. So the most efficient way to use this technique is to take into account the remainder. For example, you got a number as 0. If you divide this by 5, you will get 0 as output. Let's say then you get 1 0. This is value 2. Now if you write 2 here, 2 divided by 5 is, let's say the remainder is 3, or the mod value is 3. So you can do something to store this value 3, because when the next bit comes 0 1 0, then also this remainder will remain as 3, so that you are keeping a track of the remainder here. And let's say when again the 1 comes, you divide this value by 5, and then you will get the remainder as 0, because now this is divisible by 5, and you will produce the output as 1. So now since the divisibility factor is 5, you can have possibility of 5 cases: 0, 1, 2, 3, and 4. You can have 5 remainders. If you divide any number, any binary number or decimal number, you can have only the 5 cases. So let's start assuming that we need 5 states in this question. So let us consider 5 states. Let's take the first state as A. So here A means remainder 0, B means remainder 1, and so on. So A means remainder 1. So if the remainder is 1, our number is divisible by 5, and then we want the output as 1. So we will write A by 1 here. So this is the convention that we follow. We write the state and then slash the output. Now let's say the first number came as 0. We will start here. If the first number came is 0, then we'll move to A. Okay. Now let's say again a 0 comes. 0 0 0, whatever the number of 0 comes, so we will remain in this state, because the number is 0 and my number is divisible by 5. 0 by, let's say, let's keep it as 0.
Hello.
Now let's say, hello.
Sir, this.
Please enable the screen sharing.
Yes, sir. 1 second, sir. Sir, can you please check now?
Yes, I can. So let's continue the question. So like, I think you people might have got the idea, right, what we need to do. So you have to find the number and you have to check whether that divisibility factor, if you are dividing this number by 5, then whether the remainder is 0, 1, 2, 3, and 4. So now let's say you are in state 1, remainder 1. Now if we get a 0, 1, 0, then the number is 2, that is you have to move to state 2, because this C represents the remainder 2. Now in C, let's say you are in remainder 2 state. Now let's say if you get 1. So if you get 1, that means 1 0 1. Because this is
So can you
2
explain
and,
the state diagram again?
yeah, sorry. Okay, fine. So like what you are trying to, what we generally do is state diagram. Like we trace the state through the input. So for example, what this means is that if you are in state A and if you provide 0 input, then you will remain in this state A only. Why do you need states? To store a particular information. For example, in this problem, we need to store the information of the remainders, because we are dividing the number by 5. So since the bits are coming serially, so we cannot process all the bits coming at a time. So we have to process 1 bit, then again this bit, then again this bit, then again this bit, then again this bit. So in order to process the information correctly, you have to store information of all other n-1 bits. So that's why this is a problem of a state diagram problem. And what this convention means is, like, let's say you are in state B. So state B here means the remainder of 1. And this by 0 means it is the output. So for example, here if you are in state B, the output is 0, because remainder 1 means that number is not divisible by 5. Only if you are in state A, the remainder is 0 and then the output should be 1. Similarly, for all other state B, C, D, and we also need E also, because E will represent your state remainder of 4. So all other states, the output will be 0. So for
And the
example,
number of arrows.
arrow. So arrow represents input. So let's say you are in state B and you provided the input 0. Because you have started with 1 and then 0, that means number 2. 2 here is divisible by, so if you divide 2 by 5, the remainder will be 2. And if you are in D and you provided input 1, you will move to state D, because 1 is 3, that is divisible by, the number is divisible by 3. So the loop is not yet complete. But if you provide input of 1 to C, then you will move back to the state A, because 101 is divisible by 5. 101. 101 number is 5 also. So 5 divided by 5 is 0. 5
Sir,
divided by 5 is 1.
I have a doubt. In initial state, we have to write like reset state, right? Because here, without giving any inputs, our output is going 1 in if state.
Correct. I mean, like, this is the input. You have to start with some state, right?
Yeah.
So initially you will get a particular number. For example, you have to give a bit like, initially you are in this state only. So the initial, if you consider flock, you have to consider a state. So let us consider here, let's say you have given an input 0. So if you give 0, you have to remain in that state only. So like you can start with any state. I have just written a start for consider this example, then it will make more sense. This is the number 20. So what? So if you trace this number as 10100, so you are giving input as 1, then 0, then again 1, then again 0, and then 0. So if you trace this input here, you will eventually reach state A, that is divisible by 5. So this is your start point A. So we are considering that initially we are at 0, and this 0 is divisible by 5. I mean, it doesn't make sense that 0 to divide by 5. But for now, let's consider that 0 is divisible by 5. Because 0 divided by 5 doesn't make any sense. Okay. So and after you trace the step, you have to figure out a way कि A में अगर 0 है और 1 है तो क्या होगा, B में अगर 0 है तो 1 है तो क्या होगा, C में we have considered the case 1 है. But let's say if we get 0 after the C step, then what will be the case? So C here means 2. Let us consider an example 1 0. And if you get again 0, then this number is 4. Then that means we will move to remainder 4 state, that is E state. Hello. Hello. If you give C as 0, then we will move to remainder 4, because 100 is 4. That means remainder 4. Now if you again give 1 to 4, that is 1100. That is 12. 12 divided 5, 5 is remainder 2.
No, sir. In LSB, we have to put, right?
Sorry. Correct. So if you give 0, then 1 0 0, we have reached state 4. If you again give, let's say 1, that means 1001 means in decimal its value is 9.
9.
So 9 divided by 5 is 4. So 4 means here state D. So we'll move into this state. If my input is 1. If my input is 0, that means 1 0 0 0. 1 0 0 0 is 8. 8 divided by 5 is remainder 3. Remainder 3 means here state 0 1 2 3.
Yeah, we need one
0,
extra
1,
E.
2 3.
4
1
also.
minute, 1 minute. If my value is 9, then my remainder is 4. So that if my input is 1, I will remain in this state. And if my input is 0, then I will move to remainder 3 state.
Why, sir?
Because let's say you have got 1 0 0 1 0 0, and you have moved to state E. E means remainder 4 state, because this is value 4. 4 means remainder 4. Now if we add 1 here, that means the value is 9. 9 divided by 4, 9 divided by 5 is still 4 remainder. So it will remain in this state only if their input is 1.
Yes, sir. Got it.
If your input is 0, then this value is 8, and 8 divided by 5 is 3. Then we'll move to state D, because D represents remainder 3. Now, what else is remaining? Let's say if you're in state D, but if you get a value 1, so D में हो मतलब remainder 3 है तुम्हारा 1 1, and if you again get a 1, that means remainder 2 हो जाएगा. You can verify this. And अगर तुम्हारा if you are in state 3 और अगर input तुम्हारा 0 है, तो तुम्हारा remainder हो जाएगा हो जाएगा 1.
So if state is in D and we apply the input 0, then it code is in B. Otherwise, it will go in C.
We apply the input just a minute. इसको draw कर लेते हैं. 1 1 है, मतलब 3 है. 1 1 0 हो जाएगा. 1 1 1. 1 1 7 0 1 2. हाँ, sorry. So this 1 है. Your input is, if your input is 0, that means you will go to state B. C में input 1 हो गया, 0 हो गया. E में अगर input 0 है, E में 1 हो गया. I think the state diagram is complete, almost complete. कुछ remaining है क्या? I think the state diagram is almost complete. Let's take a number and then we analyze. Let's take a very big number, 25. So 25 मतलब this is the number 11001. So this number 11001 is 25. Now let's trace this number 1 1 0 0 1. We are back to state A. That means this number is divisible by 5. If you take any other combination, you will not reach to state A. Let's say if you take 1, 1, 0, 0, 0, that is number 24. So 1, 1, 0, 0, and 0. You will reach to state E. And E means remainder 4. So 24 divided by 5, remainder is 4. That means this state. So you can cross-verify your state diagram by taking few examples to check whether your number is divisible by 5 or not. And now to implement this state diagram into a circuit, there is a very long step. There is a very different procedure and long step. It will take another half an hour or 1 hour to explain that. So we will take it in a different session. But that is not a very big deal. First, the big deal is to make the state diagram correctly. So for now, I have shown an example of divisible by 5. For other numbers, divisible by 7, divisible by 3, the state diagram will be a bit more complicated. But yeah, the idea is more important in this case. So let's talk about another question. Is this explanation clear to you?
Yes, sir. Yes, sir.
Yes, sir.
Is the slide visible?
Yes, sir.
Can you see 4 flip-flops here? D2, D3, D2, D1, D0. Now this will be a very interactive session. I want you people to answer this question. This is a very theoretical question, but analytical question. So can you tell me what is this circuit? What this circuit does exactly?
Serial input, serial output, shift register.
Shift register, correct. 4-bit. This is a 4-bit shift register. Serial in and serial output. Okay, so I think you can get this circuit in the internet everywhere, like how this works and how this D in DQ, how the shift happens exactly. So I will come to a very tricky part of this question. Let's consider a very practical situation. In reality, this will be like some wire. This reset will be made of some wire. This clock will be made of some wire. This DQ will be a real clock made of AND gates, and we'll have a setup time, hold time constraints on all these flops. We'll have some delays of due to this setup and hold window, right? So basically, let us consider that this circuit has a problem. This shift register has a problem. The problem is that if you are giving an input D in, then you have to apply 4 clock pulses to get the output as D out. Is it correct or not? Is the statement correct?
Yes, sir.
We need 4 clock pulses, right, for this input to come into this output. So the problem in this circuit is that in 1 clock cycle only, you are getting the D in as the D out. And in register, this is not desirable. So in every clock pulse here, you need change by only 1 flop. You need only 1 flop to change particularly. But this circuit has a problem that in 1 clock pulse only, you are giving a single clock pulse, but you are getting the D in value captured at the D out value. So now you have to tell me what is the problem in this circuit. Where can the problem lies? I have told you this is a very practical circuit. You have to consider the setup time, hold time, clock, and everything, delays, and all everything that we have learned. I mean, most of the things are available in the internet and in books or everything. But let's consider this is a very practical scenario. Is the problem understand? Is the problem clear to everyone?
No, sir. Can you repeat once?
So the problem is, so what happens in an actual shift register or the shift register that we have read in our college days or in books and whatever else. So this is a 4-bit shift register. So in the first clock cycle, this D in value will be captured at Q2, Q3. If you give another clock, this value will be captured here at Q2. If you give the third clock cycle, this D1 value will be captured in D1. Q1. If you give the fourth clock cycle, this D0 will be captured into D out. So ideally, you need 4 clock pulses for this T in to get reflected, captured into the T out. Correct. This is how a shift register works, right?
Yes.
So now the problem in this circuit is, instead of giving you 4 clock pulses, what you observe that, let's say you have implemented this circuit in the lab. You have used some ICs. You have used a breadboard. You have connected this Q2 to D2, this Q2 to D1, then Q1 to D0 through wires using real wires in your lab breadboard. Okay. Then you have set the clock here. You have given a particular frequency, and then you're changing the values of D in and observing the values of D out. So what you observe that if you give a particular pattern in D in and you are pulsing a single clock, then you are getting D in reflected into the D out only in a single clock pulse and not in 4 clock pulses. So what is the exact problem going on? These D flip-flops are working exactly fine. These wires are properly connected and everything is fine. But due to the non-idealities, or what non-idealities could make this circuit work in a defective way. That is, you are giving only 1 clock cycle, but you are getting this value into the output. This is undesirable. Now, is the problem clear?
Yes, sir.
Yes, sir.
So just think about this. I'll give you a few minutes to what could exactly go wrong. I already give you a hint. You have to consider everything: setup time, hold time, and slack, and all those things that you know, like the delays of wire, net delays, everything. You can also consider the clock as non-ideal clock.
Sir, can it be like there is a setup violation, and at first flip flop only the D in goes into metastability, so we are
Correct.
getting D out.
Okay. So if violation occurs in first flip flop, then violation can also occur in the second flip flop, third and fourth flip flop, right?
Yes, sir.
So, but the pattern that you are applying in DIN, you are getting the correct pattern at the output. You are getting the same pattern at the output. The only difference is that instead of giving 4 clock pulses, instead of waiting for 4 clock pulses, you are getting the output only in a single clock pulse.
So the hold time and maybe set time is 0, like that.
Hold time, you can consider like anything, like you can consider 0, non-zero, whatever is there. But what you have to consider is that this is a non-ideal situation. This is a practical situation. Let's say you have made this circuit in a lab, or like what we do is that what we consider in general in our theoretical classes, that these have all a 0 setup time, 0 delays, everything. But for now, just consider that they have finite some delays, everything. Because in reality, we will always be having some delays. We will be having flip-flop delays. We will be having clock to queue delays. We will be having net delays.
Sir, if the clock, there is a delay in a clock, like at D2 clock, we are getting it at, for example, 2 nanosecond delay, and at D1, we are getting at 3, and at D0, we are getting at 4 delay. So first only we are getting the output at QZ. So because of that delay in that clock, we might get D out in the same cycle only. Non-ideality of clock, delay in the clock.
Sir,
Yes.
I had a doubt in the state diagram question. Can you please go to that slide?
Okay. Other, please think about the problem that I mentioned. Now, yeah, tell me your doubt.
Sir, after the B state,
B state, okay.
so can you explain how we got from B to D?
So let's say you are in state B. So B here means remainder is 1. So if your remainder is 1, if you get another one, let's consider an example. Let's say your remainder is 1. So here 0, 1 means remainder is 1. Let's say if you get another one, then this value by decimal is 3. So that means 3 divided by 5 is remainder 3. 3 remainder means state D. That's why we have moved to state D. You can take other example for remainder one. Let's say you are in your value 6, 1, 1, 0. 6 means also remainder 1. Let's say you give 1 in the input. Now what is this value? 0, 1, 2, 3, 8, 9, 10, 11. No, 8, 9, 10, 11, 12, 13. This value is 13. So if you divide 13 by 5, the remainder is still 3. So you have to move into state D because D represents remainder 13. So that's why I moved from D to D.
Okay, sir.
Is it clear now?
Clear, clear.
Now, any comments? I think one guy has already given the answer. So let me explain you this concept. Okay, something like that here. So we have 4 flip-flops in the shift register. We have clock here. We are going into all the flip-flops, and we have data.
Hello, sir. That screen is not visible, sir. We are stuck on that slide. Sir, are you drawing somewhere?
Yes, is the screen visible now? The paint window.
No,
Yes,
sir.
sir.
Slide. We are stuck on that slide, sir.
No, sir. Screen is visible.
Can you see me scribbling on the paint screen?
No, sir. No, sir. Sir, we are
We
on
can
that slide of that 4 flip-flop slide.
What is happening? Can you see the paint window now?
Yes, sir. It's now visible, sir.
So this is the clock. So the problem, as I mentioned, let's say you are applying data D. Clock look like this. So in the first clock cycle, this value will be captured here. Correct or not? Does everyone agree that in the first clock cycle, this T3 will be captured into Q3?
Yes, sir.
But due to the non-idealities, due to delays in this clock net, what will happen is when we apply this clock here, this will appear immediately into this flip-flop. But due to this net delay, this clock will appear in a bit delayed fashion. Let's say it will appear here. This is the same clock, okay? This is the first clock cycle. This is the second. This is the third. This is the fourth clock cycle. So now the first flip-flop has captured data on the posage of the first clock cycle. Now you have this D data available here at this timestamp. Now in the first clock cycle only, now this clock is seen by the second flip-flop. So in the first clock cycle only, this data will be resampled by this flip-flop and will be captured into Q2. Because we are still in the first clock cycle. And this delay between this clock and this clock is due to this net delay. And due to, again, there is some net here. Due to this net delay, this clock will also appear in the bit delayed. And due to the same reason, we'll capture this value here into this flip-flop in the first clock cycle only. Because this posage is still available for this flip-flop to capture the updated value. And similarly for the final flip-flop. So in the first clock cycle only, due to the delay in this clock cycle, you are getting an output, you are getting a single clock cycle, and then you are getting the input D in captured into D out. Only in a single clock cycle. So one of the guy has already answered this question. So is there any doubt in anyone's mind? Or is the solution clear?
Yes, sir. Clear, sir.
Clear, right? So now, if this solution is clear, now I will move to the next part of the question, that given that you have faced this problem, you have to suggest a way to solve this problem. How can you solve this problem so that this T gets captured into Q3 in 4 clock cycles?
So then we should have a correct hold time, sir, and set proper value, sir, there.
The whole time is correct. In this flip-flop also,
Synchronization. Synchronize code.
how will you synchronize? Can you just elaborate?
Once the positive edge of clocking happen in the first flip-flop, after whatever the output will capture, then it will be applied to next state, like finite state machines.
Finite state machine. Let's say you have captured this value in the first clock cycle, then you will get the output here. Then what will you do?
Then the next clock will be activate for the second flip-flop.
Correct. The clock is still available for the second flip-flop. So it will capture the value here in the second flip-flop because there is a delay in the clock. Correct. This is the problem, right? So we don't want it to capture in the second flip-flop. We want in the first clock cycle only. We don't want this updated value to get captured in the first clock cycle. We want this value to be captured in the second clock cycle. This is how shift register works. Any idea how to solve this problem? Okay, fine. What I will do is this is a very tricky explanation. It will take time for you to think about. Just draw this timing diagram and all those clocks. Try to draw 4 different clocks, give them delays and apply inputs, and try to think about this problem. I will not tell the answer in this session, but let's say you get what I will try to explain is, let's say you get some solution to this problem. Like you are able to solve this problem. If you are able to solve this problem, I will recommend to try to solve this problem again without using any AND gates, any flip-flop, any extra flip-flops. You cannot use extra anything. You cannot change setup time, you cannot change hold time, you cannot change the clock, you cannot change reset, you cannot change the input, you cannot add any other sequential or combinational elements in the circuit. But still you have to solve this problem.
Sir, we can do by just applying at asynchronous, making circuit asynchronous.
Synchronous. You means you wanted to apply different clocks to different flip flops.
Yes, sir.
No, the clock is no, the clock. We have a single source clock. We only have a single clock.
Or sir, make
How,
as output as asynchronous in terms like Q3 will be given as a clock to D2 in that way.
no, but then that will not be a shift register, right?
Yes, sir.
That will be like that will not be shift register. We want a shift register here. That will be a different functionality then. So you have to retain the functionality also. You have to retain the same flip flop. You cannot change setup, hold time, anything. You cannot add any AND gate, NOT gate, not any other flip flop, state machine, nothing. You cannot change clock, you cannot change reset, nothing. So you have to solve this problem by doing nothing. So what can you do? So you have to think about this. Just try to draw the timing diagrams and it will make more clear. I will not tell the answer now. But first of all, what you can do is you can try adding some, gates or extra elements and see how things are going to change. Just draw the timing of waveform and see how things are changing by playing around, adding another flip flop, another gate or whatever else, and then try to solve this problem without adding anything, without just in a most optimized manner. You also don't know the setup time, hold time, nothing. You just know कि ये जो clock है इसमें delay है, this net has a delay, so you cannot change the delay of this net, right? Because you don't know what is the net delay of this clock. You doesn't know the net delay of this reset, but you know कि हाँ उसमें delay है. There is also delay in this wire, but you don't know what is the delay. But only thing that you know is कि this data nets also have some delay. So think about this. You can if you are able to find the solution, you can post a message or you can.
Sir, give some more hints now.
Huh?
Give some more hints now, sir.
I've already given you hints. Like the only thing that you know here is that this D in this wire has some net delays, and this clock has also some net delays. And due to this net delays only, we are facing this problem. Correct. We also have net delays in this reset wire. You can consider that this flops will have some setup and hold time. This clock will be non-ideal and everything. You can try adding some, other logic gates, like you can forcefully add some AND gate, NOT gate, but the only thing is the functionality should be retained. So first part of this question is like try adding some extra elements to make this thing so hello everyone. So I think that I have explained the problem. So I don't have, we have already exceeded our time. So if you get this solution, just ping me or ping anyone on VLSI for all, and we will continue the session from next week.
Yes, sir.
So that's it. I still have one more question there, but we have exceeded our time by much larger amount. So I think we should close now. If anybody has some doubts or want to ask anything, please ask for any questions, any queries. I'll be happy to answer. Or else we'll be closing this session soon.